Alright, this is day 53 of Sparks Calculus. We're going to talk about the interpretations and applications of the derivative and the definite integral. So for starters, let's talk about what d dx means. So d dx of something is the rate at which that something is changing. For example, if water is being drained from the swimming pool and r of t represents the amount of water, measured in cubic feet, that is in the swimming pool at any given time, measured in hours, then the derivative, r prime of t, would represent the rate at which the amount of water is changing. So d dx of the r of t is equal to the derivative r prime of t. And since r of t is measured in cubic feet, then r prime of t is going to be cubic feet per hour. And further, the integral of the rate is going to be the amount of the change from A to B. I'd like you to take a second and see if you can explain what this value represents, and then I'm going to give you the answer. So the integral from A to B of the rate is equal to r of b minus r of a. So take a minute, pause this video, write down a sentence of what you think that means, and then I'll give you the answer. So r of t represents the amount of water in the pool, so r of b minus r of a is the amount of water that drained in that period of time between b and a. So it's the amount of the change. Let's see another way to look at this. In this table here, this is the velocity of a particle at given values of t, where t is measured in minutes. And for me, it's useful to write that a of t equals v prime of t, and v of t is equal to p prime of t, so that a of t equals p double prime, but we already wrote v of t is equal to p single prime, just for reference for me. So velocity is a rate, so when we take the integral from 0 to 30 of the rate, that's going to be equal to the position at 30, subtract the position at 0. So this is the amount of change of position from 0 to 30. So that's this first part. Oops, I didn't put units of measure. What are we doing? This is in feet per minute, so in feet. So now we have to go find it using a midpoint Riemann sum. So I see three nice intervals between 0 and 10, between 10 and 20, and 20 and 30, where we can use the midpoint at 5, 15, and 25. So the integral from 0 to 30 of vt dt is going to be equal to, let's see, rectangles with a width of 10. So 10 times the height, 1.6, plus 10 times the height, that 3.1, plus 10 times the height, that 1.6. And doing the arithmetic, we've approximated this to be about 63 feet. So we see it's the area under the curve here. That's how we calculated it, given the numbers in our table. And this is what it's representing. So now let's try finding the integral from 5 to 25 of the acceleration. And just like we did above, where we worked backwards, took the antiderivative of velocity to get the position, we're going to take the antiderivative of acceleration, which is velocity. So we get v of 25, fundamental theorem of calculus, and v of 5, which we can get right from our table. So v of 25 is 1.6, and we subtract v of 5, which is 1.6, which we get 0 feet per minute. So in feet per minute, what does this represent? This represents the change in velocity from t equals 25 to T equals 5, which you can see, average there was no change. Let's try some examples. Next page. The temperature of water in a tub at time t is modeled by a strictly increasing, twice differentiable function W, where W of t is measured in degrees Fahrenheit and t is measured in minutes. So W of t equals temperature at t minutes. If we take the derivative of that, we're going to get the change of the temperature. And then W double prime of t would be how fast the rate of change of the temperature is changing. Rate of change of temperature. You might be able to say that a little more succinctly. Something about how fast the rate of change of temperature is changing. I don't know. You'll probably do better than I will. So, using the data, we were asked to estimate the value of the rate of change. So this is really the slope at 12. We don't have 12 on here, but we do have 9 and 15. So we can take the average. So we can say that W prime of 12 is equal to W of 15 minus W of 9 over 15 minus 9. W of 15 is 67.9. W of 9 is 61.8. We do the arithmetic and we get about 1.017 degrees, and we are in Fahrenheit per minute. And what this means is that at t equals 12 minutes, water temperature that is to see is changing at a rate of 1.017 degrees Fahrenheit per minute. Now we're asked to find the integral from 0 to 20 of the derivative, W prime. So we have to take the antiderivative of that, which is going to be W. And we're going to evaluate that at 0 and 20. So that is W of 20 minus W of 0. At 20 it is 71. At 0 it's 55. Which gives us 16 degrees Fahrenheit. And what does this represent? This is the amount of change in temperature from t equals 0 to t equals 20. In degrees Fahrenheit. The next part says from 20 to 25, the function W that models the water temperature, so we're talking about W, has a first derivative. We're given the first derivative. So we're given the rate of change of the water temperature. Based on this model, what is the temperature of the water at time equals T equals 25? So if we were to take the integral from 20 to 25 of W prime of t dt, this is going to be equal to W of 25 minus W of 20. And we don't know all of that. I believe we know 20. So this is W of 25 minus W of 20, which if you look back at the table, you get 71.0. So what we're looking to solve for is W of 25. In order to do that, we need to know this value right here. 0.4 square root of t cosine 0.06 t dt, and we don't know how to take the antiderivative of this. And I haven't shown you how to do that in your calculator, which I promised in the last video I would. I'll make sure I upload a YouTube video. It probably won't be mine because I don't have access to a simulator on this computer. And it's really not that difficult. I'm going to go through real quickly how you would do that. You would plug this into one of your y values in a graphing calculator. So say y1 equals 0.4 square root of t cosine of 0.06 t, and then you would go to second, calculate. I can't remember what that is. It might be the window button. So it's the second, oh no, it's trace, I believe. Second trace, and if you scroll down, because this is calculate, if you scroll down, you're going to find something that looks like this. So when you hit the calculate, you can see that there is an integral button like that. And then after you do that, it's going to graph your function, and then it's going to bring you to a screen that says lower limit. And our lower limit is going to be 20. And then ask for the upper limit, which is going to be 25. And then when you hit enter, it gives you an answer for the area under the curve, and it should even shade in the function. So it's kind of cool when you have a colored calculator to get a bunch of them shaded in. And we ended up with 2.043. So if I'm not able to simulate this for a video, I will find one so you can see really what it looks like. But that's how they get that answer. And we know this is equal to 2.043, but it's also equal to w of 25, which is what we're looking for, minus w of 20, which is 71. Then we can work backwards and we can solve for w of 25. We end up with 73.043 degrees Fahrenheit. Alright, I'm going to do one more example, and I am going to use the calculator. Anything that looks this messy, we have to find the integral of. It's probably going to require use of a calculator. So we have a pan of biscuits removed from an oven at which point in time, t equals 0 minutes, the temperature of the biscuits is 100 degrees Celsius. The rate at which the temperature of the biscuits is changing is modeled by the function b prime of t equals negative 13.84 e to the negative 0.173 t. So we're asked to find the rate of change at 3, and we have the equation, so we need e prime of 3, which is equal to e to the times 3, and we put that in the calculator, and we will get negative 8.236 degrees Celsius per minute. So what does this number represent? This represents that at time equals 3, read minutes, the temperature is decreasing by 8.236 degrees Celsius. And now we're to sketch the graph of b prime of t, which is right here. So you can do that on a calculator and get something that looks like this. So not only are we asked to sketch it, but we're asked to explain in the context of the problem why the graph makes sense. So when you look at this, we have time increasing, and actually the rate is increasing as well, but it's everything's negative. So why does that make sense? Well, think about what we're talking about. We're talking about biscuits taken out of the oven, put in room temperature. So they were 100 degrees when they came out of the oven, and then the rate of the temperature should be decreasing. So biscuits taken out of the oven should be decreasing in temperature. At least until they reach room temperature. So B prime of T should be negative. And the graph of B prime of T should be below the x-axis. Alright, at time equals 10, what is the temperature of the biscuits? Well, we do not have B of T, so we can't plug 10 in, but we do have B prime of T. So we take the antiderivative, and we know B of 0 is 0, and then we go to 10, because that was the one we need, of B prime of T dt. This is going to be equal to B of 10 minus B of 0. And we know B of 0 equals 100, so B of 10 minus 100 is going to be equal to this. So again, we're going to put that in our calculator. So y1 will be equal to the function B prime of T, which was negative 13.84 e to the negative 0.173 t. So that's going to go in our y1 or any of our y's. And you're going to hit second trace, which is the calculate feature. And from there, you're going to scroll down until you get to this button, and then it's going to graph. And when it graphs it, you'll see the function, and then it's going to ask you for a lower limit, which is 0, and upper limit, which is 100. And when you do that, you're going to get that is equal to negative 65.817. So we get 0 to 10 B prime of T dt, that is equal to negative 65.817, which is equal to B of 10, which is what we're looking for, minus 100, because we know that, and we solve that for B of 10, and we get 34.183 degrees Celsius. And the last example on page 530 is your discussion page, so you're going to put that into Haiku. And I will see you next time.